Hey, hi everyone. Welcome to this first video of this Atcoder weekly series. So in this particular video, we're going to talk about this average median problem, and we're going to deep dive into how we can kind of solve this problem and formulate it for coding. We're not going to code it up, so that's going to be a separate part that you have to do as an exercise after this video. But again, this is a very interesting problem, a very nice problem on a particular topic. So we're going to deep dive into that. But before we move on forward, so this is going to be the first video of this whole series, weekly series, where we're going to be talking about, let's say, having one problem of Atcoder, leetcode, and then codeforces every week. And these are going to be cherry picked problems which are going to have some tweaky ideas that if you don't know, you should definitely learn up, right? So there's going to be few agendas. One is to obviously understand the problem, then finally code it up. Second is every problem I'm going to talk about few small subtleties in its reading phase, in its like observation phase, and then its formulation phase. After every video, make sure that you comment below the one thing that you kind of loved and learned through this particular video, because that's gonna like keep it in your mind for a very long time. Whenever we write a particular learning for us, it kind of persists in our mind for a longer duration. So just make sure that you note down what is that one learning that you learned from this particular video and post that up in the comments. And I feel a lot of people, if they comment up, there's going to be a good kind of learnings summary kind of created out of the videos, right? So this is something that we can kind of collaborate and create together. So do definitely comment up on what you learned from this problem. Let's start with the problem. So the problem is average and median, and this particular question says that there are n cards, ith card, and every card have an integer ai. We have to choose any number of cards. Like, however, for every card I, at least one of ith and I plus 1th card must be chosen. So out of every two neighboring card, at least one of them has to be chosen up. Okay. Then we have to find the following values. One is the maximum possible average of the cards chosen with the given restriction, and maximum possible median of the cards chosen with the given restriction, right? And median is the n by 2th seal smallest of them. And this is there. Yeah, cool. So we need to find the maximum possible average and median with the restriction that neighboring items can be taken up. So that's our current understanding. So that's what we have read. Now, while in the reading phase itself, we understand that, okay, there is going to be 10 power 5 numbers. So we don't really have some possibilities of some random technique like DP or so, because the number values are pretty high as well. Then we have the numbers. This is the input format. Fine. Let's have a look at the sample. 6, 2, 1, 2, 1, 1, 10, 4, 2. So the maximum number of average that we can take is kind of pick up the maximum elements. Second, fourth, and sixth card makes an average of 12. Yeah, so these three makes an average of 12. Yeah, makes sense. Yeah, so that's 1 plus 1 plus 10. So we are kind of taking up at least one of every neighbor. And 1, 3rd, 5th, 6th card makes a median of 2. Yeah, that's also correct. Right, so these are the best things that we can kind of make. So our understanding is correct. One thing that I note while reading phase itself is that the number, the average can be floating point as well. So we need to have some precision. That is 10 to the power minus 3, right? Cool. So this is the first thing that you kind of do in any problem, which is read the problem very carefully, you understand the problem very well. That is finding maximum possible average and median with this restriction that out of two cards which are neighbors, one has to be taken for sure, right? So that's the problem. And let's move into, let's say, solving this particular problem. So we have this flow that we follow for any problem. One is, first of all, read it correctly, read one sample, understand the problem. Next, we try to kind of observe. You can also say that we are kind of solving the main problem, right? And then the third phase would be to formulate on how should we write the code the best way possible. Now, in this particular problem, we see that n is up to 10 to the power 5, right? That n goes to 10 to the power 5, and values are pretty large as well. So the possibility of doing some sort of dynamic programming reduces then and there, because pretty high for that. Then we are kind of left with some ideas. So what I generally think of at times where there are these kind of problems, where you have to find some optimal value, mostly it's some sort of problem solving paradigm problem itself, that it's going to be either, let's say, brute, right? There's going to be either some greedy strategy, right? It can be some sort of divide and conquer or binary search, essentially, right? Or it can be a DP kind of thing, or there might be some involved maths, right? And when I say greedy, I'm kind of including the ad hoc portions into this itself. Okay, so it has to be one of these only. Like, somehow we have to find some way to kind of generate the best, right? And whenever we first of all see that we have, like, there is this setup, right, that you have these numbers over here, and out of the two you have to take one of them, right? So there is this very classical DP problem which says that, okay, in an array, when you can when you have to take elements out of the two neighbor ones, there is this very common problem that find the maximum sum of elements, maximum sum of an array of elements, such that at least maximum sum of array subset with at least one of two neighbors taken. The same restrictions as this problem, that out of two neighbors, one has to be taken and you have to maximize the sum. Now, this is a very classical DP problem. If you have not solved this, you can also think about this in terms of DP, that okay, maybe what we can do is like the choice to take this or not take this depends upon whether we have taken this element or not. So essentially this is kind of a form 1 DP where we kind of iterate from first element to the last, and DP of I comma 0 tells you that okay, we can kind of take this element and we like I comma 0 means what is the best we can do from the ith element till the end. This is the ith position till the end, such that the last element has not been taken. So if you have not taken the last element, then you will have to take this. If you don't take it, then two neighboring elements were not taken, right? That contradicts. So in this case, we will have to take a of I gets added plus now the last element is taken going forward. So we can call dp of I plus 1 comma 1, right? And if we have dp of I comma 1, then we think of that last element was taken. So we have an option to take a maximum across two, which is a of I plus dp of I plus 1 comma 1, that we can take it, or dp, we don't take it, dp of I plus 1 comma 0. So out of this, take a max. So this is a possible kind of solution for getting the maximum out of elements, where maximum sum out of elements where you cannot leave two neighboring items altogether. But again, this is not really feasible in this problem because we are asked for medians and means, right? Mean depends upon the number of element taken, and it is not really obvious that we're going to have like a definite amount of elements, right? Maximizing the sum is fine, but when you're choosing some elements, there are few kinds of restriction in this problem. One is that neighboring one. Next is that you have the sum by count as the final metric, right? Let's focus only on the mean right now, right? So based on the choices of elements, you will also have to keep track of this sum and count. So we can maximize the sum for a particular count, but in that case, you will have to include the count in the state of the DP. But again, if you include the count, then it becomes n squarish, which is not going to pass for this problem, right? Because the constraints are too high. So initially you think of DP is possible to maximize the sum, but it's not feasible to solve the main problem with this. So we eliminate it off, right? So we are going with elimination kind of idea. We think of maths. Maths doesn't really help us in this problem because like obviously there is a restriction that we have to take subsequences, and numbers can be pretty much anything. So maths doesn't really help us. Brute enter end of 5 doesn't really seem good. Greedy, right? So there can be a greedy strategy or there can be a binary search. Now, here is where experience comes into play, that when you see this problem and you have this mean kind of a construct, you need to understand that this type of problems are specifically solved by problems of binary search, right? This is a very special class of problems of binary search. So this comes from your previous memory of solving something similar, right? But whenever we are dealing with mean, binary search is something that can keep in place, that we can keep in the place of any other paradigm. Why is that so? Because there is this simple reduction that, let's say there is this A1, A2, A3 element taken up, AK, right? So these are some elements of the array. These are not the first K, these are any K elements. So when you do the restrictions, let's say that these elements satisfy the restriction that was given to the problem, and then we will have this K, right? Now this is the mean, right? Now, if you go back to this whole setup and we are saying that, okay, let's try to solve this with binary search, we will make a construct, okay, f of x, right? This is the check function, will tell us, can we make my answer, okay, or the mean, let's say greater than equal to x, right? Can we make mean greater than equal to x, right? So if you think about the whole space of numbers, right, like the real number space, right, you have this x naught, which is the maximum possible answer, which is the optimal answer. And for any particular number on this side, you can say that, yes, you can make anything bigger than that, because we know that optimal can be created, and anything on this side is no, right? So this is something where it comes into, where the monotone space comes into action. So if you have not seen something like this is called monotone space. You can read up about these things online if you want to. But this is how you can think about binary search problems, that you have an x naught and you have to check, you have to find this out. On one side, every value kind of gives yes or no, right? If we can formulate this function f of x, so can we make our answer greater than equal to x, yes or not? Till x naught, all of those would be yes. After that, everything will be no. And we need to find the last yes in this whole formulation. So when we have this kind of setup, we are, it's possible to use binary search, provided that we can like devise these functions, right? And actually for means we can do this. Why? Because when we say that this is equal to, let's say, greater than equal to x, okay, so this is also kind of parallel to a simple reduction. Let's kind of cross multiply this, and I'm going to write it in the next page, which is a1 plus a2 plus a3 so on up till ak is greater than equal to k times x, right? In the previous page we have k multiplied with x on this side, right? So there are k terms over here, and it's k into x. So I'm going to take kx on this side, and it's going to be minus kx, and we're going to subtract each x from each of the terms. So I'm going to write a1 minus x plus a2 minus x, right? So on up till plus ak minus x is going to be greater than equal to 0. Now this is what we need to check. Like, checking this is same as checking this, right? So essentially asking that, can we make the answer or the mean of a subarray like which satisfies, right? Which obviously satisfies greater than equal to x is same as, if we subtract x from every element, can we find a subarray or the a subsequence of the whole array which satisfies the given condition and has this condition, right? Now let's term these numbers something like b1, b2, so on up till bk, right? And can we find, like, when we are doing binary search, think about it. When we are doing the binary search, we know the value of x, because like it's the low plus high by 2, mid is the current x. So we have to write this check method, right? When we write this check method, we kind of see that, okay, this is going to be b of k plus is going to be greater than equal to 0. And then for this particular sum, we see that, okay, it's actually possible. How do we check this up? So we need to get this new array b1, b2, b3. So anytime any element is being chosen up in the set, we know the value of x because it's given by the binary search. It's the x that we are currently checking, right? These elements come from the array, and k is something which is dynamic based on the number of elements getting selected. But once we switch it to this, there is no k, like it can take any number of elements, right? So we need to find in this new bk array. So there is this new b array where you subtract x from every element, and you have to find that there is this array which is b, where every b of I is equal to a of I, right? Let's say the a of I is the original array. We have that given in the problem, minus some x, which is the current binary search value. And in this, can we form some subsequence such that no two neighboring elements are left out, right? And the sum of that is greater than equal to 0, right? This is what we need to find. So we need to find some subsequence where no two neighboring elements are left out and their sum is greater than equal to 0. A very neat way to do that is to use the same starting DP solution that we devised, that, okay, find out this neighboring, find out a subsequence whose sum is maximum. So if there is a subsequence which has the maximum sum and that is not greater than equal to 0, then there is no subsequence, right? So just find out the maximum sum subsequence across all, and then we can kind of find out this greater than equal to 0 part, right? That's how this is going to work. So this is how it's going up in my mind, like how do you formulate this up, right? Obviously, I'm explaining a bit more on this particular video when I'm going to code this up. Like if I'm solving this in contest, I'm not going to be thinking of all these steps because I know that this is how you reduce the means, right? And you can simply replace it with this in binary search. But this is how it works behind the scenes. So we kind of see that, okay, this is a of I equal to a of I minus x, and we have to choose a subsequence with no neighboring element left out and having sum greater than equal to 0, which is same as find the max and check if it is greater than equal to 0 or not. Because if the max is less than 0, then nothing can be greater than equal to 0, right? And we have to just check if there is any one solution. Because if there is any one subset which makes this feasible, it makes this feasible, which makes this feasible, right? And if it is feasible, then that particular thing is a yes, or else that is a no, right? So this is how we formulate binary searches in general. This is how binary search can be thought in a generic way. Maybe I will make up another video which is going to kind of explain how we actually solve any problem of binary search in this formulation. But anyways, this is something that we can skip off in this particular video, or else it's going to become very, very long, right? But anyways, this is there. If you guys need that particular video, like mention in the comments that, okay, this is some topic that we can take up binary search specifically, right? Cool. This is the main binary search part, so binary search is applicable in this. If I think about the time complexity, we will have the answer somewhere. It's an average, right? So it's going to be 10 to the power 9-ish, right? Log of that range needs to be there, and we can kind of keep some n. Like the checking part is a linear DP, so this is n comma 2. This is a linear DP, right? There are n into 2 states multiplied by 1 plus 2 transitions at max, so it's order n, right? This is a formula that I'm using from one of my previous DP's videos. So if you have not checked that out, check out the DP video on my channel. So this is almost something that can pass, right? So this is feasible solution for now. So binary search can be used to find out the mean, right? Let's move on to median, which is again very interesting. So we need to now find the median of the whole array. What is the answer for that? And we can use a similar approach again, that, okay, is my median, again we will use binary search. If my median is greater than equal to a certain value, x or not. So again, for this kind of a setup, we can think of that, okay, there is going to be an optimal, and this is something that we can create. So this is the optimal median that can be created. And fx says that if, can we create a median greater than equal to given x or not? Can we? It's a yes or no question, right? On any number on this side, we're gonna see that, okay, median is gonna be yes. On any number on this side, it's going to be no. Now, one thing I note about this problem is that there is this median is always going to be an integer. So we do it in an integer space rather than on a floating point space, which was true for this number, right? This mean. So we just do it in an integer space, and that's not much of a difference. You can have a look at any code. It's going to explain up that. Okay. And this is there. So we need to find median greater than equal to x or not, yes or no. How do we check that? Can we make a median greater than equal to x, yes or no? So again, if median is greater than equal to x, right, and we have seen that, okay, the n by 2 seal element has to be there. So if there is like exact split, this is the element that has to be there. And if there are like even odd number of elements, something at the center is going to be the median, right? Okay, so how do we use the same restriction and can't check, can we make median greater than equal to x or not, right? So think about this. Every element that we choose, which is greater than equal to median, right, is gonna go on this side, right? This side of the thing. Any element which we take, which is greater than equal to median, is gonna go on this side of the selected elements, because it's going to be sorted. And in the sorted one at the middle, we need to find the median. So on this side, and anything that is less than median, right, it's gonna go to the right, and this is gonna go to the left, right? So we need to make sure that there is at least, there are more elements of this type than this type. Then that particular x is feasible, right? I mean, if we want to make all the elements bigger than equal to that, like if we want to get median greater than equal to a particular value, then this line should definitely skew on this side, right? Not on this side. Let me quickly give you an instance of this. Let's say we have 1, 2, 3, 4, right? And we have some partition over here. So this is the current median, right? So the elements that are bigger than equal to this, that are greater than equal to the current checking value, right? The higher the value, the more favorable they are. So we will replace them with plus ones. And what we can do is we can replace these elements with plus ones, and we can replace these elements with minus ones, right? And now we can think of this problem in a different way. So what we can think of is, we need to find the median greater than equal to certain x, right? So for every element greater than equal to x, it gives a +1 to the contribution. And every element which is not bigger than median gives a -1, right? And at the end, if we now in this whole subarray, we need to take some things like this, such that like that initial condition is not violated. So plus greater than equal to x is replaced by +1, or else it's -1, right? And we need to find elements subsequence whose number of +1s is more than -1s. So essentially we can say that sum of a of i's, sorry, the after transformation, let's call this any array b of I. So b of I is nothing but a of I is greater than equal to k or not, is greater than equal to x or not, right? Just check this. If it is true, +1, or else it's -1. And then sum of b of chosen i's, okay, chosen sum of our chosen b's has to be greater than equal to 0, because if there are more numbers greater than equal to x, then at least the median is going to be x, right? And we have a better chances of making a bigger median. So this is what we want to do. So now if you again use a binary search, you know the value of x, you can transform that array into plus minus ones, and then we want to find some subsequence whose no two neighboring elements are left out and the sum of elements is greater than equal to 0. If we have to choose it in that particular way, we just think about, fine, go ahead and let's say take the maximum one. Let's find out the maximum sum subsequence which has the given conditions, and if that is less than 0, then there is no feasible solution, or else there is at least one feasible solution, so that's a yes. Check the max. If greater than equal to 0, then yes, or else no, right? That's how we do it. So if we go back, once we create this B array, check it using binary search, that whether, check using DP, that whether there is a subsequence which has sum greater than equal to 0 or not. The maximum one, just find it out and check if it's greater than equal to 0 or not. And if there is, then there is a suitable solution for this condition, or we can actually fill out these elements with all medians greater than equal to x. So we can make median greater than equal to x, which means this is yes. So we are on this side, or else we are on this side. Accordingly, we can do the binary search, right? And then we can find the solution. So again, for median also, we can use the same kind of a formulation again, that we have to find the maximum sum subsequence with no two neighboring elements left out, right? So now if you think about what all things we have done in this particular problem, we have used a very similar technique. Every time we are using a binary search on the answer, so we are finding out the answer using binary search. And now if you know the answer in the binary search, you are just checking whether that particular answer is feasible or not. And we want to when we want to check it up, for mean, we are kind of having this transformation that subtract every element, that guessed mean with every element, and then can we make a subsequence with sum greater than equal to 0 with the given restrictions, which is a solvable problem in order and using DP. Again, when we are talking about median, again we are transforming using this new function for every element, and then we need to solve the same problem, that subsequence sum with no two neighboring element left out having sum greater than equal to 0, is it possible or not? So for mean and median, when you have to maximize them, this is the technique. So this is something you can keep in mind. So next time you're going to see a problem where you have to find the mean maximized, do a binary search. When you have to median maximized, do a binary search. So this is something which you can actually use in any such problem where there is some complicated restriction in the array, right? This check method is devised because there was this DP possible in the check one, right? But again, for any general technique, this is a general technique. So you only know this if you kind of have solved something before, to be honest, that if you have solved a problem where you have transformed it this way, then only you kind of know about this particular technique. But again, it's a very neat one, right? So this is the whole like observation part of the whole problem, right? There are a lot of things kind of what we did, but if we kind of try to summarize, number one, we, for mean and median, we are two different processes, right? So for both, we are doing binary search on answer, right? Let's say that is x, right? We want to find, so from we create an B array where where b of I is going to be a of I minus x, right? And then in this array, a particular x is feasible or not is given by that problem of, let's call this as a separate problem as maximum subsequence sum with no two neighboring left out, right? So this is what we can check for this B array, right? Similarly, for median, we can kind of go into a similar direction, that we do a binary search on answer. Note that there is a subtle difference between these two sides. This is going to be a binary search on floating point numbers, because mean can be a floating point value, but median is again always like an integer, because an array has integer values. So this is going to be something which we can do on median, on integers. Okay, it's an integer range, so lows and highs are going to be integer value. These are floating values, right? So you can do a finite number of iterations, though those are implementation level details. And then for every b of I, we're gonna have a of I greater than equal to x or not. If when you're checking for a particular x, it's 1 or 0 or minus 1, and then it's again the same problem altogether. So there is this one problem that you're solving, which solves both the problem, but the transformation is a bit different, and idea is also like, the idea is same, binary search on answer, but then transformations is different based on mean and median. This is something you have to keep in mind going forward if you have not seen a problem similar to this one before. It's a very, very nice idea, and this can be repeated off again. I've seen problems of similar kind before in different sites like CodeChef and Codeforces also. So this is a very neat idea. And once we know this thing, like both of them works almost like in n log n, so that should be sufficient, n log a of I, which seems to be sufficient for this problem, right? Because it's n into like 10 to the power 5 into log 10 to the power 9, 32, right? So this is there. And this linear DP is something that was feasible. So you need to know many things for this problem, that linear DP is feasible to find maximum subsequent sum. Then you have to know this transformation of this mean. You have to know this transformation of median that we kind of discussed. So these are few learnings that you're learning in this problem. So make sure that you keep these things with you when you solve the next problem of similar kind, right? So this is the whole observation part. Now you have a full solution. So next what we can do is we can go ahead and try to solve this problem. But again, a small tip whenever you're kind of going into solving the problem, before that there is this step. So if you go back to the main problem, main stuff, this is going to be a formulate step, right? You have to formulate the whole solution, right? When we want to formulate, we want to think of the code, how it's going to show up finally, right? So let's go back. Let's say we want to formulate now. So the way we're gonna do this is take this is something which takes around 1 minute. Take A and then we do a binary search, then build a B, and then for both of them we need to solve the same problem, and elements are going to be like floating points itself. So what we can do is we can create a function which takes B and gives the maximum subsequence problem, subsequence 1. So get the func of B, like create B with that transformation with A of I minus X, and then func B has to be greater than equal to 0. And then again there is another binary search for median. We transform B with A of I greater than equal to X based on this plus 1 minus 1, and then again use the same function. So once you have thought of this kind of structure a bit in your mind, then you can go forward with coding it, because this will save you a lot of time. When you copy paste the same stuff written over here into this part, you can make a simple mistake in that, and that will kind of ruin your, let's say, score, because you might make a mistake, right? So thinking about this formulation step is something which I feel can help you in a lot of problems. Maybe it takes like 1-2 minutes in every problem, but in that one problem where you might have wasted 30 minutes, it can save you a lot of time. So this is something how you can formulate the code, and rest is just coding. So that's the place where I'm going to stop over here to discuss about this problem. You can think about, build up on this a bit more, think about this problem, read editorials, read codes, and then follow up and solve this problem. But make sure that you comment up what is that one thing that you learned about from this particular video, so that that persists in your mind for a very, very long time, right? This is a very, very nice problem. Make sure that you solve it irrespective of whether you kind of solve any other problem or not, right? So that's going to be all for this particular video. Thanks for tuning in, and I hope this content is something that you are enjoying. If there is some suggestion that you want, like make the pace, like make more easier stuff, which I'm not really inclined to, but if a lot of people kind of, if you are the kind of judge on what kind of things can be created, but like if you have some suggestions for me for this channel for the problems, the way I explain them, you can go ahead and tell me up in the comments. I would be more than happy to include them if I find them suitable enough. And do like the video if you found it to be value for the time, and subscribe to the channel, because there is going to be like a leetcode weekly going up on the Thursday, and there is going to be codeforces questions on Saturdays, so don't miss them out. Press that bell icon because the notifications are important. You guys forget these things, and please subscribe. I think a lot of people who watch the channel are not subscribers. Please do watch them up. Okay, so fine, thanks for joining in. Bye bye, see you in the next video.